and then gravitational field as we go. So we'll start off by by looking at the basic physics of circular motion and how that works and how you create centripetal force and things like this. Okay, so let's start out with a little picture here. Let's say that we have, let me use my circle here. So there's my center. Oops, not big enough. Okay, so we've got a circular motion, and we'll have some radius, we'll say, out here like this. And okay, we have this radius here in some circular motion. Okay, we're going to have some object here. Say it has some velocity as it's going around in the circle. We'll call it V. Okay, and if we want to get the centripetal acceleration of objects going in a circular path, okay, they accelerate not because they're speeding up or slowing down in their magnitude of their speed, but mainly because they're constantly turning in a circle. So that constant change of direction will cause an acceleration as well. So you can get centripetal acceleration, we'll call it AC, which is vector, and that's basically equal to the square of that velocity on the edge over the radius. So the smaller the radius, the higher the acceleration is going to go, right? The larger the velocity, the higher the acceleration is going to go. So we call this the circular acceleration, okay, or centripetal acceleration. Okay, we'll just call it in a circle. So that's meters per second squared. This is our velocity on the edge. Okay, and that's going to give us meters per second. So when you square it, you get meters squared over second squared. And of course, this is radius in meters. Okay, so that gives us our acceleration. And we also know that the force, according to Newton's second law, the net force is equal to the mass times the acceleration. Okay? So if we wanted to come up with a circular acceleration, we could put this acceleration in here. So you could get a net force that's equal to the mass times the velocity squared over radius. And this is the force, okay, of the object in a circle. So centripetal force. Oh, can I move my head? Yeah, good idea. Sorry about that. All right. So if I plug in this value here for acceleration, this would be a circular force or centripetal force. So it's basically a force in the circle. So there is a force, and if you're swinging something over your head and then you cut the string, it's going to be pushed straight out. Okay? So that centripetal force is going to be opposite of gravitational force if you're thinking of a planet. So think of this like a big planet and something going around it. Okay, so that velocity is going to keep it that centripetal force is going to push it outwards, and the gravitational mass of the planet or the moon or whatever is going to pull it back down. And when those things are equal, that's when we have a stable orbit where it's going around and around. It stays in the same distance from the Earth. Okay? And that's kind of how those two things work together. And that's how we're going to end up getting an orbital velocity and an orbital period. Okay? Now, there's all kinds of questions we can do with centripetal acceleration and stuff like that, but we'll kind of skip through that, and we'll look more at knowing that once this force of moving in a circle or centripetal force is equating to gravitational force. And that's kind of how we derive, the period of a satellite going around the Earth in an orbit, the orbital velocity of a satellite going around the Earth. Okay, so we're going to be looking at man-made satellites traveling in orbit, basically, for these next two things. Okay. Okay, so this is, we're going to look at, basically, we'll look at the centripetal force balancing, we'll say, gravitational force. To get a stable orbit. So when if I ask you later in the unit, how do satellites stay in orbit? Well, they stay in orbit because their velocity traveling around in a circle gives them a centripetal force that counteracts the gravitational force of the Earth. And they try to balance it out to stay in that orbit. Okay, and sometimes they have to do a little bit of correcting with thrust and things like that. Okay, anyways, we're going to look at these two. Now, these formulas seem quite complex because they have a lot of variables in them. And we're going to look at how we're going to equal gravitational force to our centripetal force. Okay, so let's draw another picture and let's derive a formula for orbital velocity. So we're going to be trying to find this orbital velocity. So let's do that. Okay, and I'm going to flip the page here. Okay, so finding orbital velocity. Okay, we're talking of satellites. Okay, so first of all, we know that the acceleration, we'll just do it. We did that already. We'll do the force. The force in a circle, we'll say, okay, is equal to the mass of the satellite times the velocity of the satellite squared over its radius. Okay, so this is going to be our mass of our satellite. And that doesn't actually matter, as you'll see when we start deriving the formula, the masses will cancel. So let's do the Earth here. So let's draw the Earth. Center of the Earth. The Earth, and let's see if I can, we'll put a satellite around this Earth. at some orbit. Okay, so that blue circle is going to represent the orbit of a satellite. So here's our satellite. Okay, so let's put it on, let's draw it in blue here. Okay, and it's got some radius, okay, and there's going to be a force of gravity, okay, and then there's going to be an equal force of, sorry, I kind of drew through that, the centripetal force. The force in circles, which we know is already that. Okay, so now the force of gravity we can calculate by using universal gravitation. Okay, so that's this satellite in orbit. Okay, that's a satellite. I should have wrote it here. Okay, and we have an equal force of in a circle, centripetal force, and a force of gravity keeping it in this orbit. So this blue is our orbit. Around Earth. This is Earth. Okay, then we don't. Okay, so how do we get our satellite? So let's get our force of gravity. Force of gravity is equal to big G, remember, times the mass of the satellite times the mass of the Earth, okay, divided by the radius. Okay, squared. Okay, and that's kind of why I know one student yesterday, I forget who it was, my apologies, asked about, why we use R instead of D for this. And mainly because we're doing a lot of orbit stuff around planets and stuff like that. And so it tends to be very traditional that they use an R down here rather than D for distance between two objects. We don't often do a lot of work with universal gravitation that doesn't involve a planet somehow. Okay, so we're going to say that this and this are equal to each other. So this is just our mass of the Earth. Okay, and this is our radius of the orbit. Okay, from the center of the Earth. Okay, and this is the mass of the satellite. It's the same, right, for both of those. So you can see that the mass of the satellite won't affect it at all in terms of finding its orbital velocity, which is what this is going to be right here. So we're going to solve for this by equating these two equations together and rearranging it and seeing what we get. If that makes any sense. Okay, so let's equate the two. Okay, so I'll do this here. So we're going to say that FC is equal to Fg, which is our gravitational force. Okay, so let's plug in this one. Okay, so we've got on the left side this one, mass of the satellite times the velocity of the satellite squared over the radius of the orbit. Okay, that's on that side. And then on this side, we're going to put the blue of the gravitational force. I should have made this black, apparently, so that we could have the centripetal force, or this green, I guess. So this would be big G, gravitational constant, mass of the satellite, mass of the Earth, or the planet or moon if you're launching a satellite around a different one, over r squared, the radius. Okay, so now let's do some canceling of this to figure out what our equation would be. Okay, well, we have mass. This is all multiplied and divided. This is all multiplied and divided, so they're all one term. There's no plus sign, so we don't have to do any factoring or anything like that. So we can cancel out the mass of the satellite on both sides. So I'll use green for some canceling here and working this through. Okay, so this is gone. So what does that tell you? That tells you that the mass of the satellite has nothing to do with its orbital velocity at all. Okay, and we have one radius over here and two radiuses over here. So we'll cancel the one radius here. That makes that a 1. And we'll cancel, there's 2 r's here. We'll still be left with 1, so we'll just cancel the square. So this leaves us with v squared, the velocity of the satellite around this, in this orbit, squared, is equal to big G times the mass of the Earth times the radius of the orbit, okay, how far above the center of the Earth it is. So that's a pretty easy formula. So if we want to get the orbital velocity, we have to kind of square root all of this because of this square. So our final step would be to square root this. So this is, so the velocity of the satellite equals the square root of these numbers. Now, often it could be the mass of the moon as well. It doesn't always, you could have satellites around the moon, but most of the time it's around the Earth, right? So it could be a different planet if we make up one with a different planet, but we'll just say Earth over there. So this is what our orbital velocity would be. Okay, now the orbital velocity, our typical metric system velocity is meters per second. Okay. Okay, G, we know what G is. G is always the same. Okay, and we'll put it later. This is the mass of the Earth. And that's a constant, even though, you know, you'd think it would change a little bit, but in relative terms, not really. So the mass of the Earth, and that's going to be in kilograms. And it's a constant. And this is our radius of the orbit. And that's in meters, okay? And then we have big G. So we know that this is 6.67 times 10 to the negative 11 Newton, I always forget, let's see, Newton meters squared, kilograms squared. Okay, has to be able to cancel those out. And then this is our orbital velocity. So that's kind of how it works. Now, where do you get the mass of the Earth? That's basically a constant. Now, you have to be careful when you're doing radius because you have to add, there'll be some height above the crust of the Earth plus the diameter of the Earth. And then you have to make sure that you put it in meters because of the newtons in here and the meters in here and the kilograms in here. That's our standard metric use of that. So we'll do an example of an orbital velocity, how we could get an orbital velocity at a certain height. Okay, so let me dig up the information for the constant of the mass of the Earth here. We'll just quickly do a little, and then we'll do orbital period after that. Okay, so let's move this down slightly. And then we'll ask a simple question. We'll keep that there. Let me type it so it's neater. Okay, so I got the mass of the Earth here. Okay, so let's say, what is the orbital velocity of a satellite oops, don't need an I in there, whoop. There we go. Okay. Of a satellite that is 220 kilometers above the Earth's surface. Okay, we need to know some constants. We know that constant value. So first of all, the radius of the Earth. Okay, if we look up the radius of the Earth, okay, gotta get our Google out here. All right, so the radius of the Earth is about 6,378 kilometers. Okay, at polar radius, 6,000 something. The mean radius. So we'll use the mean radius. Okay, so we'll use 6,370 kilometers. 6,370 kilometers. Okay, and then the mass of the Earth. Okay, we'll look that one up as well, and we'll use the best estimate of that. All right, so it's 5.972 times 10 to the 24 kilograms. Okay. So let's use 5.97. We'll use three significant figures because I used 3 for this one. That one only has 2, but let's make it 3. So we'll say 0.0. Okay. So this one will go as 5.97 times 10 to the 24 kilograms. Okay, and this is scientific notation. Okay, so we looked up our values. Now, generally speaking, when I give you questions like that, sorry, unrelated question here. Sorry, I missed that earlier. How did they measure the radius of the Earth? Okay, the first time they measured the radius of the Earth, they used it, they basically looked at, they were doing Romer, I don't know if you know, but there's a guy named Romer, and this is way back in the 1600s. And what they were doing was they were looking at Jupiter and Jupiter's moons. So what happened was they knew, at the time they were wondering about speed of light and things like this. So they were observing the moon, one moon of Jupiter, and they observed the moon of Jupiter when it was on the far side at certain times, and they observed the moon of Jupiter when it was on the close side of Jupiter. And how they figured that out is they kind of basically were able to figure out in between the time delay that happened in there. And so they could figure out kind of what the distance was to a rough approximation. It wasn't a very accurate measurement at that time, but it was fairly accurate. And that was still when people didn't believe that the Earth was round. So there was people that were trying to prove that it was round and things like that. So that was one way. Later on, when they were technologically wise now, we have things like lasers and things like that, and it's pretty easy for us to measure just the radius of the Earth. And it varies, of course, right? Because of the crust of the Earth being, because the crust of the Earth basically has mountains and things like that. So so this would be an average, basically, kind of how that works. So it was related to the speed of light and all kinds of, and a lot of observations that they did. It's kind of the same way that they figured out the mass of the Earth. All right, so let's do a calculation of this. So we have to be careful because we have to change it to meters. So the first thing that we know is we know what G is already. So we're good there. The mass of the Earth we know. That's this 5.97. Okay, and the radius we have to calculate by taking the 6,370 kilometers and adding it to the 220 kilometers. And then we have to convert it to meters. So if we add 220 kilometers to that, that's 6,590 kilometers. Or, okay, there's 1,000 meters per kilometer. So we add multiply by 1,000. Okay, so if we want to write this in scientific notation, that's 6.59. So we're here. So 1, 2, 3, 4, 5, 6 times 10 to the 6th meters. Okay, now we can apply our equation. And we'll get this value in meters per second. So it should be pretty fast, you would think, to be orbiting the Earth. So our orbital velocity, it's a square root of 6.67 times 10 to the negative 11 kilometers, or sorry, not kilometers, newtons per meter squared, kilogram squared. Okay, times the mass of the Earth, 5.97 times 10 to the 24 kilograms, divided by, this is all under the root sign here, divided by our radius here. So our radius was 6.59 times 10 to the 6th meters. Okay, so we're going to end up losing, because of the newtons, we're going to end up losing a kilogram there, and newtons is if you remember, it's in meters per second squared times kilograms. So the other kilogram is going to go, and a meters per second is going to go, and we're going to be left with meters per second. This is going to be meters squared, second squared when we're done. And then when we square root it, it'll give us meters per second. Okay, take our calculator out, we'll do the calculation. So, let me get the calculator here. Okay, so we're going to go 6.67 times 10 to the negative 11, okay, times 5.97 to the power of 24, okay, equal. So I got my top that looks, oops, let me put my brains back in there. Okay, so that's my top value. I'm not going to round off till the end. Then I'm going to divide by 6.59, okay, scientific notation, 6, equal sign. Okay, and I get a really big number, and then I'm going to square root it. So I get about 7,773. So if we go to 3 significant figures, I get 7,770 770, so 3 sevens, sorry. Meters per second. Okay, so that would be our orbital velocity. That's, you're flying around there at a fairly quick rate around there. Okay, now if you do that and look at that one, and you think about that in kilometers an hour, it's fairly fast. So that would be, so if you think about kilometers an hour, there's like, if you go kilometers per hour, you know there's 3,600 seconds in an hour, and then there's 1,000 kilometers per meter. So you multiply by 3.6 to figure it out. So if you take 7,770 times 3.6, you get about 28,000 kilometers an hour for that orbit. Okay. Okay, there is also something called orbital period. Now, orbital period is a little bit different because the period, I'm talking about the time it takes to do one revolution or one revolution of the Earth as you go around. And the period formula comes from other math formulas that we really haven't looked at probably in your math career yet. Okay, so we're going to kind of look at orbital period, but I'm not going to derive it like I did this one with just these two. This was easy to derive. The one that we have uses a different formula. It kind of uses the period formula, okay, around something. So I'm just going to state the period formula in this case, okay? And then we'll kind of do an example of that. We'll calculate a period in this case. What would the period of this particular orbit be, okay? So underneath here, let's extend this a little bit. So the orbital period okay, so we're going to call orbital period, because in physics, period is a capital T like that. Okay, so that we'll call it orbital period. So basically, acceleration around something, it uses pi's because we're doing a sphere, or we're approximating a sphere. So I'm just going to state it here. So the orbital period is 2 pi. That comes from being a sphere, and it's the square root, and this comes from Kepler's laws, if you ever want to research it. It's r cubed, right, divided by g times the mass of the Earth. And we're basically going with the mass of the Earth again. So this is still our radius, this is still g, this is still the mass of the Earth. This is just 2 pi in front, and this is our orbital period. And this comes out in seconds, okay? So you're going to get a fairly big amount. So what is the orbital period of our satellite? So what is it from the satellite above? So we already know everything there. Let me move my brains again. Okay. So we know this, we know this, and we know this, and we just have to plug it in because we kind of figured out all those things already. So let's move that up to the top here. Okay, so we'll be looking back. So we got 2 pi to start with out here. Okay, the orbital radius that we had, we calculated it in meters, was 6.59 times 10 to the negative, times 10 to the 6. So we're going to plug that in. And it's cubed, by the way. So be careful. And I wish I could, well, we could probably derive it, but the math would be beyond kind of what we do here in physics. So there's no need. Okay, and then we know what G is. I guess I got to put it around both the unit and that. Okay, and then we know what the mass of the Earth is. Okay, so we want to find out what everything is and then multiply by 2 pi under the root sign. So the first thing I'm going to do is I'm going to cube the top. So 6.59, scientific notation 6, cubed. Okay, so that's going to give me a number. Now I'm going to keep that on there. Now here's a trick that you can do. You don't have to multiply these before. You can divide them out each separately because multiplication and division happen at the same time when you do order of operations. So you can go divide by 6.67, scientific notation negative 11. This is a 4. Right, same as up here. Same as this one right here. Good question to ask. Okay, so then we'll divide, equal sign, and then we'll divide again. 5.97, scientific notation 24. Okay, when I do all of that, I get about 718,713, like this on my calculator. This is before I square root it. Okay, so now I'm going to square root it. Okay, so then I'm going to square root it, so then I get a number here. Square root. So this is 847.8. Okay, and I'm just going to leave that on my calculator. That's after I do all of this, right? I've got this on my calculator. Right? I'm just going to leave it there, and I'm going to multiply by 2 pi. So I'm going to go times 2 pi. Times 2. And where's my pi button on this calculator? There it is, but how do I get to it here? Shift pi equal. Okay, so after I do that, I get the orbital period at about 5,000, and we're going, again, 3 significant figures, so 5,330 seconds. So if you're thinking there's 3,600 seconds, 5,330 divided by 3,600 seconds in an hour, that's about 1.48 hours. So about an hour and a half to go around the circumference of that orbit. Okay, so that orbital period, I know we only did one example here with it. This is orbital period. Now, the formula for orbital period, we didn't derive it because it's a little bit more complex math in terms of what we said in there. Now, you can also have different planets. So the mass of the Earth could change if we talk about the mass of the Moon, or if we're putting basically a satellite around the Moon or something like that. Okay, so that would be a little bit different. Okay, let me just look up and see. Yeah, there's different, we'll be using different ones when we look at that. Okay, so that's where I'm going to stop today. In terms of how they found the mass of the Earth, that's kind of the same thing that if you think about Cavendish's experiment, he was actually trying to find the mass of the Earth when he did that, or get an approximation for it, and he actually came up with big G instead, and then he could figure it out from there. And you know, in terms of the first talking about Romer and finding the radius of the Earth, I think the Greeks also made a measurement way back in the day that was totally based on the curvature of the Earth, but nobody believed it because they still thought the Earth was flat back then. So, you know, you can always do some research on that, and it'll definitely tell you that as well. Okay, any questions? I think I'm going to stop there today because we're going to get into a new topic tomorrow. We're going to be looking at gravitational field strength. All right, so we'll see everybody tomorrow. Bye-bye.